In these next couple examples, we're going to be thinking about the derivative as our instantaneous rate of change. So let's look at this first example here. In a metabolic experiment, the mass m of glucose decreases according to the function m of t equals 4.5 minus 0.03 t squared, where m is measured in grams and t is the time in hours. Find the reaction rate m prime of t at t equals 1. So we need to start off by actually finding the derivative m prime. So this is the limit as h approaches 0 of m of t plus h minus m of t all over h, which is equal to the limit as h approaches 0 of 4.5 minus 0.03 t plus h squared minus 4.5 plus 0.03 t squared, and then all over h. Right, and it looks like we got plenty of room here. So we have the limit as h approaches 0 of 4.5 minus 0.03, and let's go ahead and multiply t plus h by itself. That's going to give us t squared plus 2th plus h squared minus 4.5 plus 0.03 t squared all over h. And then this is equal to the limit as h approaches 0 of, and you can already see we're going to lose a few terms here. These 4.5s will have a minus 0.03 t squared. That'll cancel with this. And so let's write what we're left with. So it looks like a minus 0.06 th plus, and actually let's make that minus 0.03 h squared all over h. And then this is equal to the limit as h approaches 0. And right, we could factor an h out of the numerator here. Let's actually do that in this step right here. So if I factored an h out of this, I would lose this h. This would just become an h. And then this is all times h. And so our h's cancel, and so we're just taking the limit of minus 0.06 t minus 0.03 h. And if we let h go to 0, this just becomes minus 0.06 t. And now that we've found our derivative, we can find what we were looking for. We were looking for m prime of 1. Okay. So if we plug in 1, we just have minus 0.06 times 1, which is minus 0.06. And I want us to think about what this number is actually telling us. So if you remember the units for the derivative, they're the units of y over units of x, or in this case, the units of m over the units of t. Let's go figure out what those were. So m was measured in grams, And if we look up here at t, that is in hours. Next, let's try and interpret our derivative here. So is what we might say is at the instant, t equals 1 hour, the amount of glucose is decreasing by 0.06 grams per hour. Let's go ahead and take a look at another application to instantaneous rate of change. And specifically, we're going to be looking at the relationship between the position, the velocity, and the acceleration. Okay. So if s of t is the position function, then the velocity at time t equals a is given by s prime of a. And you might actually remember this. We were estimating the velocity at a point by trying to estimate the slope of the tangent line at that point, right? We were looking at the slope of secant lines between 2 points that were really close. Okay. And so that's really what our derivative is. Okay. So then, well, if the velocity is the rate at which position is changing, well, what do we call the rate at which the velocity is changing? That's kind of an interesting question. Well, that'll be the acceleration. And actually, let's change that notation for a second. Let's just write this as v prime of a. All right, and so velocity, this is how fast we're going, and acceleration is how quickly our velocity is changing. Acceleration is that feeling maybe when you're in a roller coaster and you change speed really fast and maybe you feel like your stomach drop. Okay. That's that acceleration, quick change in your speed. I want to point out the units for both of these as well. So when we're talking about velocity, we might be in maybe meters per second, right? This should be the units of s over the units of t. So units of s should be some way of measuring distance, meters, kilometers, feet. And then units of t, these are going to be units of time. So maybe seconds, minutes, hours, so on. Okay. But when we move down here, well, velocity is already measured in meters per second. But if you find the rate at which that's changing, then it's what you're looking at is meters per second per second. Or sometimes we'll write that as meters per second squared. Let's go ahead and do an example. Example 6, a rock is thrown upward from the top of the Empire State Building. Its height in feet t seconds after being thrown is given by s of t equals 1002 plus 30t minus 16t squared. And the first part of this asks us, when does the rock reach its maximum height? So first of all, this thing right here is a downward facing parabola. So it's going to reach its maximum height up here. And let's think about what happens up here. We end up with a horizontal tangent line, don't we? Okay. So what that means is right here, right at that point, the derivative must be 0, right? We have a horizontal tangent line. Horizontal tangent lines have a slope of 0. We want to find when s prime of t is equal to 0. So that means we're going to need to find that derivative first. I'm going to skip the work here this time just so you don't have to watch me do this again using the definition of the derivative. But if we went through the process, we'd get 30 minus 32t. And so it's just this that we want to set equal to 0. All right, and we can add the 32t over and divide by 32. All right, and we could divide both of those by 2. We'll get 15/16. And this is measured in what? T is measured in seconds.